Ray marching is an algorithm for rendering signed distance functions onto a 2D screen. It is done by marching a ray from every pixel on the screen and checking if it has hit an object in our scene. However, this makes it inefficient as many nearby pixels would actually execute the same calculation, making it redundant. Cone marching comes along to resolve that, where instead of marching a ray every time, we march a cone instead. In this video, we'll discuss how exactly we can do that, and we will build on the previous video where we implemented ray marching. So if you haven't watched that, pause this video and come back after. Also, if you want easy access to the code and more elaborate explanations, you can check out my article on my website about cone marching. Let's go over the algorithm very quickly. Instead of marching the ray, we march a cone. Simple as that, and the math behind it boils down to when we stop the marching. For ray marching, it's when we hit an object, but for cone marching, it's when the hit radius is less than the cone radius, meaning that the cone has hit something. And implementing cone marching can be done in many ways. The first one, and the one discussed in the only PDF I could find online, is a multipass approach. But in this video, we'll make a simple vertex fragment shader in three.js. More details about the PDF will be in the article. In this simple approach, we subdivide the rendering plane into smaller square subdivisions, cone march as much as possible there in the vertex shader, send that data to the fragment shader, and then ray march one last time in the fragment shader to see the hit position. We do this by first changing how we define the marching plane in three.js and update the uniforms to include a camera FOV and the number of subdivisions we are using in the scene. Then we create the cone marching function, which again looks exactly the same as the ray marching one, with the difference being the end condition of the marching loop. We also need to update the ray marching function to accept a starting distance in order to use the marching steps in the cone marching function. Finally, we have the shaders. In the vertex shader, we calculate the ray origin and ray direction for the specific vertex, find the distance from the cone marching, and send that to the fragment shader. In the fragment shader, we take that distance and use it in the ray marching function, and as a result, we can get a significant increase in FPS. Though cone marching can improve performance, it is dependent on how much the SDF is occupying the screen and how close it is to the camera. That being said though, in some instances, it can significantly increase performance to a substantial level. In my game Fractal Glide, for example, this optimization was essential, as I wouldn't have been able to create the complex levels while keeping the performance at least 60 FPS. Thank you so much for watching, and if you have any questions, you can join our Discord and ask me there, or contact me through my various social media accounts. Until next time, bye-bye.